Okay, so let's get started. All right, your question before we start, yes, please go ahead.
Since we don't have on-site today, could we ask a few questions about lab number 2?
Sure, so we could certainly do that. So first of all, thank you for coming. It's an extra lecture, so it's extra effort to come, so I appreciate that you took the time. But before we start, since there are no office hours, we can also spend a few minutes talking about lab 2 and anything else that you need to ask about. Yes, please.
Cool, I'll start it off. So the catalog server is supposed to have two functions, update and query, as REST endpoints. Is it okay to decompose both of those into query by topic, query by item, and update stock and update cost?
Yeah, so I think that question was on Piazza. I don't know if it has gotten answered or not. So my take was you get to design the REST API. So if you want to take the basic interfaces we have specified and make variants of it, perfectly fine. You could also have REST API calls where if you could say update and then whether you're updating the stock or the price is actually a parameter. So it's part of the URL. So you'll have /update /stock and then so you could specify it that way. You could also do it the way you said. So of course that should not be an issue. You can do that.
Gotcha.
Right?
So there's some degree of flexibility in how we design the REST endpoints.
Yes, I think that that's certainly a lot of flexibility. I mean, you, so long as you stick with the basic design we have left. I mean, we would like you to understand what it means to design interfaces as well, not just we specify it and you go with it. So yes, we will let you do some of these things if you want to.
Cool. One more question. Do we have to do, and I think you said this last class, do we have to do any synchronized access to the database? Because right now there could be some problems
Right.
in my implementation.
So that's a good question. The question is whether to do any synchronization and things of that sort. So technically you are not writing a full-fledged database. Okay, you're just using a file to act as a database. At the same time, as you realize, there will be race conditions. If you're checking the stock and you're buying at the same time, you could have problems. Typically, you would use transactions to avoid that, but there are no requirements to do transactions. You could simply use locks, Python or Java locks in your code. If you so wish, that will give you correctness. But if you don't, then you should at least explain that we did not actually implement any transactional semantics. But it is very straightforward to just use very simple locks to avoid. And this could be lock on the whole file, which means you're locking the whole database in some sense. That will give you it won't give you much concurrency at all, but it will at least give you correctness. So you could do simple things of that sort, but if you don't, at least say that you did not actually implement anything complicated in terms of transactions. So that should be fine.
Gotcha.
Okay. Any other questions on the lab before we move on? Yes. Okay, question is what do you put in the persistent data? So think of this as a database, right? If you had a store and you had a database, what would you put in the catalog? And the catalog would be number of the items, the item code, the price. So when you search, you say these are the products I'm selling. Right? In the order database, you would put here's an order, you have an order number, and then you'll have some details of the order, and so on and so forth. Right? So those are the things we are expecting you to do. Now, if you could separately log requests that are coming in, but they don't have to be that is just to show your code works. Right? You don't necessarily have to put all those details in the database. Okay, so maintain it the way you would normally do it for a store, a web store. Okay. Yes, question?
So if I had my servers running on the same machine, I could write shell script to start all the servers at the same time. But if they are residing in different machines, is it possible? So two questions. One, is it possible to write a shell script to start all of them at different machines? And if not, can I write specify in my documentation that let's say orders go to headlab 1, catalog go to headlab 2, like that?
Right. So the question is, you should have one script that will start everything up, or can you have one script per machine where you have to first log in and do it? You could do it either way, but you need to document it saying here are 3 scripts, log into node 1 and then use this script to start the front node and log into another node. That's perfectly fine. Having said that, you can of course automate multiple one script starting off multiple processes on multiple machines. You could simply use SSH to do that and specify the command and it will just do it for you. There are other scripting techniques like expect that do this. You could use those more advanced techniques, but the simple thing is fine as well.
Just one last. So if you use SSH commands, that would mean that you'd have to expose your username and password.
Question is, do you have to use your username or password? No, you don't need to. You can just basically specify the node name. But so if some other user uses it, it will use their username to do that. You don't have to actually put your password in there. Please don't do that. And don't then put it on GitHub, which is even worse. Okay, yes, please.
So for the order table, or however we're persisting the orders, should we only be persisting orders that are successful or orders that are unsuccessful as well?
Okay, so the question is, I think that also been asked. Question is, should you put failed orders? It's clear that you should put successful orders, right?
Sure.
You could put failed orders. That's up to you. Some stores would do that just to figure it out. Some stores would actually write that into an error log saying here an order failed, and then have somebody else go and look at our orders failing, because failed orders are only used for debugging. Right? Why are they failing? Are we out of stock? Is there some software issue and so on? Technically, you don't need to write them to the database, but if you log them somewhere, there's could be a log file that's completely independent of your database. Every system has logging capabilities, right? So you could write it to an error log. You could ignore it. That's fine too, so long as you don't let erroneous orders succeed. That's what we care about.
Perfect.
Okay. Yes. Any other questions? Yes.
I use a database, so on the description, it says probably the catalog server connect to the database. Can I do, have my own implementation that use the order server to also connect to the database?
Yeah, the question is, if you use a database, can you have both the catalog and the order server connect to one database? Is that your question? Yeah. You could do that. The way we had suggested it, you should have 2 databases or 2 files. But certainly then if you add a database, you have yet another tier. It might just complicate things. It may be simpler to have, if you're using SQLite, for example, just have one database one for a catalog server, one for an order server. That's better. Because then if you have yet another database, then you'll have to write a way to access that database from the processes that are catalog and order servers, right? Because we are not assuming they'll be on the same machine. SQLite is a file that has to reside locally on that machine. So you got to deal with that issue. Okay, does that answer your question? Yeah, okay. Any other questions? Yes, last question. Okay, question. So, right. So the question is, can you do you have to have a database text file? So and have a log file in addition. So what we suggested was you actually don't need to have a SQLite or any other database. You could just have a file which has maybe CSV values or a JSON object that you can parse that acts as your quote unquote database. Okay. You could also use a regular SQLite file. That's fine. In either of those 2 cases, you are going to keep the actual information in the database. If you want to show that your code works, you are presumably going to print something. There's no other way you would know that. So those log messages could be saved in a text file, and you can say here is the output of the catalog server, order server, etc. Because most systems actually have logging capability. So you are just adding that just to show that your file, your system works. Yes. That's right. So you could keep the database separate from the log file. Don't confuse the 2. That's all I'm trying to say. Okay. So logging is just to show your code is working or to debug. The database is actually used for the system itself. Okay. All right. Anything else? Yes, please.
Can you talk a little bit about testing and how you would go about it? Because more than designing the system and like getting my code to run, I felt like testing was the most hard part for me because I didn't know what exactly I'm supposed to test and how I would go about testing individual components.
Okay, that's a good question. The question is on testing. So the thing you have to keep in mind is once your code works, you still have to write some test cases to make sure you can test your code and convince someone that it works. You have to do performance testing to show that it actually has reasonable performance. We have no performance requirement, but other than that, you actually test the performance of your system. So there are all these extra things to do, but coming back to the testing question, testing distributed systems actually much harder than testing a single program, okay, because there are many simple frameworks you could use to do that. Having said that, you got to design some test cases, right? The test case would be you could test for error conditions, just as an example, right? So you say I am going to ask for an item that does not even exist. What does it do, right? I set the stock of an item to 0. I ask for that item to buy that item, show what it does, right? Then you could say that I send multiple concurrent requests and it should do something reasonable. You can have 2 clients and something. So you can construct simple scenarios to show that it would have the desired result, right? And that is all we are looking for right now. In this case, there are 3 components. So you could even say I'm testing the catalog server separately by just sending a simple client is making the request rather than the front end making the request. So we could do any of those things. We are not expecting anything complicated other than that you should know how to think about testing distributed systems. Okay, yes.
For the performance testing aspect, would you expect just like here's the number of milliseconds that running these different calls takes, like API calls on a different server takes, like after
Right.
20 times, something just average that out or something?
Right. So the question is for performance test, should we just take some average and present that average? So I would say yes, but that's not enough. We are not asking you just to measure one thing. We are asking you to actually think about how you would also change something and see how the behavior changes and make a plot. You can say I had 1 client, I have 3 clients, I have 5 concurrent clients, and then did that make a difference, right? So when the load goes up, in your concurrency, the load is going up. If you're making sequential requests till 1 client, there's only 1 request being processed in your system. So thinking about, I mean, that is how you would actually do a actual evaluation, right? So how does the behavior change over the system? So expect to do some very simple things, but put some graph or a bar graph or a table that shows I varied something and actually looked at how the behavior changed. It's not that I just run 1,000 requests and I give an average. That is what you do for one of those bars maybe, right? So that's the general way to do it. Okay, so let's get started with the class lecture itself. So today we are going to switch gears, talk about consistency and replication. Okay, so there is some material here which may be not that easy to understand. So please feel free to ask questions because this may be concepts you never heard about or thinking about it is not the easiest. As you will see, there are some subtle things that you will come across when we talk about consistency models, but bear with me, hopefully you will at the end of the class still get some appreciation of this issue. Okay, so first of all, now we are going to start thinking about distributed systems that have replication. This is the first time we are starting to talk about this issue. We have talked about many other things, but not really talked about replication. So we are going to start with this notion of you can replicate the data in your system, you can replicate the computation in your system. In fact, in your next lab, that's what you will actually do. You'll take the system you built now, we'll have multiple replicas of the database or the computation and show that that gives us better performance or some other property that becomes better. Okay. Now, there are many reasons to do replication. Okay. One is, of course, you can scale the system better because a single machine or a single copy of any computation can only scale to the based on the resources of that one machine. But you have n machines and you are replicated on those n machines, you can hopefully harness the memory and the computational resources on multiple machines. Okay, that gets us better performance. You also get better reliability because if you have one replica that goes down, the other replica is still up and it can continue to serve requests. Okay, so typically you will see these two reasons for replication. Anytime you see a system using replication, it's either to have better fault tolerance or reliability capability, so you can tolerate some crashes or other kinds of faults, or it is to get better performance because a single machine is not adequate for whatever it is that you are doing. So, you will see these two reasons why you are doing replication in the system. Okay? And replication can actually take many forms. You can just replicate on multiple machines in a LAN. You can also replicate in a wide area. Okay, so, you will see when we talk about things like web proxies, you are actually replicating, but the replicas sit on machines that are far from one another, sort of distributed over the internet. But when we talk about replicating, let's say web servers, you are going to replicate on multiple machines on the same LAN. Okay, you can also replicate across, but that's how you might typically build a simple replicated web server. Okay. Now, there are many issues you will have to think about when you think of replication. Okay. So, one is how many replicas do you need for whatever it is that you are doing. Okay. So, if you are trying to design this for fault tolerance, you want to tolerate crashes, you will probably at least need 2 copies, so that you can tolerate 1 crash. Okay. But if you want to tolerate k concurrent crashes, you will need k plus 1 copies. Right. So, the number of replicas you need is going to depend on what is it that you are trying to do. And the same holds for performance. Okay. You will have to see what is the workload you are trying to service and how many machines do you need to service that workload, and that will tell you the degree of replication. So, the degree of replication is going to depend on what level of fault tolerance you need or what type of performance you are trying to get. Okay. And then there are other issues of where should the replicas be located. This might matter if you are actually going to do things what are called geo-distributed replication. You are actually putting replicas in different places, different location. Okay. And that also has many interesting issues that you have to think about. So, let's say you are building a game, right, an online multiplayer game, and you want to replicate the game servers. Okay. So, typically then you have to ask where are the game clients, where are my users. Okay, and then you want to put your replicas as close to the users as possible, because they would like, when you are gaming, you want low latency access to whatever you are doing, because you want to use speed in order to win. Right. So, where do you put the replicas is very important in these kinds of cases. You have to think about where the requests are coming from or where the users are located, and where can you put replicas to satisfy your user needs. Okay, so, there are many issues, and some of this we will come back to when we talk about web. Okay, we will take the World Wide Web as a very specific example of a large distributed system and think about replication and these issues in that context. We will not talk about it more broadly for any arbitrary system. Okay. But instead, what we will do today is think about what extra work you have to do if you have replication. So, we will assume that there is replication. You have decided how many replicas, where to place them, and so on and so forth. But then what does that mean? What additional work do you have to do? And that additional issue is one of consistency. Okay, if you are replicating your data, okay, say, then you have multiple copies of it. If you update one copy, the other ones become outdated. Okay, so how do you ensure that they are all in sync with one another? This is the problem of consistency. Okay, so you want to ensure that all your replicas are consistent with one another. Okay, so and so we will look at many different types of guarantees you can provide on consistency, because consistency tends to be expensive. We will see that maintaining consistency is not as easy as it would seem. Okay? And what property do you want to provide to your, or what guarantee do you want to provide to your users, and what techniques could you use to actually provide those guarantees. Okay? So, that is the kind of discussion we are actually going to go into. But before we start talking about consistency, there is another issue that I want to talk about, which is the relationship between consistency, availability, and what is called network partitioning. Okay? So, if you have a system that is distributed, okay, ideally you want to keep it consistent, all the copies of the system to be consistent from one another. Okay. You also want the system to be highly available, which means if there are some faults, you would like to tolerate it. Okay. And you want partition tolerance, which means if there is a network fault, the system should still continue to function. Okay. So, these are all good properties to have in your system. Okay, so consistency, which says the nodes see the same data at the same time. If there is a change, all the nodes see the same consistent data. Availability, which says if some nodes fail, it does not impact the rest of the system. And partition tolerance says that essentially if there are network problems, network reliability issues, there's a problem with the network, the system can still continue the function. The nodes are up, but the network is partitioned or parts of the network are down. Okay. Now, there is this theorem called the CAP theorem, which you should all at least know what it means and what it is about. So, though this theorem is it started off as an observation, okay, but it's still called a theorem. Okay. And what it says is, given any distributed system, okay, if you want to achieve these 3 properties, you cannot do so. You have to actually pick any 2, okay, because when you pick those 2 properties, you essentially lose the ability to provide the 3rd property. Right. So essentially the theorem is saying that it's impossible in a distributed system, or it's impossible for a distributed system to provide consistency, availability, and partition tolerance all at the same time. Okay. So you have to pick any 2, which ones you care about, and you are going to lose the 3rd one. Okay. So he started off as an observation by a computer science researcher from, is a faculty member at UC Berkeley. He made this observation at a talk he gave, and then lots of people thought about it and then said, why is this the case? And they figured that that's actually indeed the case. And eventually there were some theoreticians who said, under these scenarios we can actually prove that that is the case. So now then it actually became a theorem, which is now called the CAP theorem. Okay. CAP is an acronym, as you can see, stands for consistency, availability, and partition tolerance. And I'm going to give you some examples. Okay. So there are systems that will give us consistency and availability, but they assume that the network is reliable. They don't actually work when the network is not reliable. Okay. Things like distributed databases and so on actually fall in that category. Okay. We talked about there's 2 copies of the database. We sent the query to both copies and had them perform transactions. We assume that the network was actually reliable. If the network is not able to send certain requests to one of the copies, you cannot actually, it doesn't work anymore. Okay. So it gives us consistency, okay, because you are ensuring that all requests are being processed by all replicas. It gives us availability, which means if one replica goes down, the other one is still functioning. So it can continue to serve requests, but it is not tolerant to network faults, okay, in that particular case. So we got 2 of the 3 properties for that system that we studied. Okay. And then there are other techniques. So when we did things like distributed locks and pessimistic locking, okay, we were able to get consistency. You could track the state of the lock consistently. We even got some partition tolerance. There are distributed locks that give us partition tolerance, but availability is not going to be guaranteed. If some replicas go down, you cannot actually, especially when you did majority voting and things of that sort, certain number of replicas went down, you couldn't figure out what the state of the lock was. So we lost that property. Okay. And we haven't talked about web caching and things of that sort, but but we did talk about DNS very briefly in one lecture. And what you will realize there is DNS gives us high availability. There are many DNS servers, they're replicating data and so on. If some of them go down, you can go to other servers, they'll still serve the request. Okay. And it has good partition tolerance. The network is down, they can still continue to service requests, but what it doesn't have is consistency. Okay. Consistency is very weak in DNS because you can make a change to DNS, it can take up to 24 hours for that change to propagate. Until then, replicas are out of sync. Okay. So that's an important thing to keep in mind. Okay. And the very high level thinking is, the way you should think about it is, you could say, why is consistency hard to achieve if there's a network partition? Okay. So let's say there are 2 replicas. You make an update on one replica. Okay. Now, if you want to keep the 2 consistent, you have to tell the other replica that I have seen a change and here is the new version of the file or whatever it is. Now let's assume the network is down. Okay. The network is down. By definition, the 2 replicas cannot communicate with one another. So you can't do consistency, because consistency requires that you are able to communicate. right? So you should see that there's automatically a tension now between consistency and network failures. Okay, you can only get one of the two. I mean, if you are actually tolerant to network failures, that by definition means that some copies will get updated and other copies are out of sync until the network partition failure goes away, then they can become consistent. So you will lose consistency temporarily, but you are tolerant to network fault. But if you want to keep things consistent, then you will basically say, okay, I cannot assume that the network is faulty, because the only way I can keep my replicas in sync is the network is always up and I can propagate all the changes immediately. Right? So that should give you just one simple argument that tells you why there is a tension between these two. So you can take any pair of those properties and make similar arguments as to why you cannot do one or the other under certain conditions. Is that clear? I mean, that's not a proof, but I'm just giving you some intuition of why you can only get two of the three. Okay? And the best way to think about it is consistency and network faults don't go well with one another. If you have a network partition, you can't keep your replicas consistent because messages cannot go through the network. Any questions on this? Yes?
Can you just explain once again what is partition tolerance?
Okay, what the question is, what does partition tolerance mean? Okay, so I'll go back to explain that. Okay, so there are three properties. Consistency simply means if you have multiple copies, they are all in sync. Okay, if you make change in one place, the changes propagate, every copy is in sync. Okay. Availability says that if some nodes fail, other nodes can continue to take over that job and continue to system as a whole. So availability looks at failures of nodes. Network partition tolerance looks at failure of the network. Okay, in this case, the nodes are up, but the network is down. In the other case, some nodes are down, the other nodes and the network is up. Okay, and then consistency essentially says the copies are all in sync. Okay.
Would partition tolerance imply consistency in some way? Aren't those two related?
Okay. Question is what the question is partition tolerance same as consistency?
No, it relates to consistency. If you don't have partition tolerance, then it is not tolerance toward if you have a network issue.
Yes.
Then you won't have consistency, right?
Yes, so that is what I was saying, that consistency and partition tolerance don't go with one another. If you want perfect consistency, you have to assume that the network is up. Because if the network is down and two copies are on the two sides of the network, this side of the, I mean, let's say you broke a link. So this side of the network is up, the other side is up. So you can make a change here. Okay, now that copy is out of sync, so you are no longer consistent. Right, so that's.
In the first case, when you say there is consistency and availability.
Yes. So this means that you lost network partition tolerance.
So in that case, even your consistency is lost.
No. So I think that you can have, if you assume no network, if you want to tolerate network partitions, you will lose consistency, which is the case here. So these systems are not strong, don't give strong consistency, but they're highly tolerant to partitions. You can have local instances that are still serving requests. Right? Your local DNS can serve requests even if your link to the internet has gone down, for example. Right? So that's what it is saying. Yes, question.
Consistency plus availability, network plus then means like cluster databases plus network to the client.
Can you repeat the question? I didn't understand you.
Network for a single database, what does it mean? Network data, so partition tolerance.
Right. So if your single database, partition tolerance is not required, right? I mean, you're losing. You can't access the database if you are partitioned. The clients are not able to access the server. Yes, in that case, right. Question.
Can you explain why the seventh
This one? Okay. So what we are doing here is in the CAP theorem, we said there are three okay. So what we are saying is in the CAP theorem, okay, you can get two of the three properties. Okay, there's another picture I'll show you, then we'll come back to this slide. Okay, so this may not be hard. Don't forget about all these things. So what you see are three properties. Okay, consistency, partition tolerance, availability. Okay. It says for any system you design, any distributed system you design, you can pick two. And you lose the ability to provide the third property. So if you say I care about consistency and I care about partition fault tolerance, the theorem says in that case your system cannot provide you availability guarantees. Or you say I care about partition tolerance and I care about availability, then your system cannot provide you good consistency guarantees. So it says you can only get 2 of the 3 in any system that you design. And by definition you cannot provide the third. And this is just explaining systems where you have picked those 2 and those systems give you those 2 properties but not the third. In the case of what you were asking was consistency and partition tolerance, it's saying that these systems like distributed databases and locking do not giving you availability guarantee, okay? But they can give you some consistency and partition tolerance guarantees. Okay? And then in this case, you are essentially losing consistency. You are giving weak or no consistency guarantees, but you are giving availability and partition tolerance guarantees. That is what it is saying. Yes, your question.
How is the, in the first example, this consistency plus availability, how is the state database consistent with the network database?
So question is how is consistent, which you are talking about the first.
Database, how it will be consistent if there is a network failure?
You are actually assuming the network is perfect. You lost the network ability to tolerate failures in this case. You are only getting availability and consistency.
If you have a network failure, it's tough to get consistency. So in cluster database, when databases are linked in a cluster, they have to connect via network.
That's exactly the yes. So the point is that you are assuming there are no network failures in this case, which is why you are getting consistency. Because I'll drop the partition or the network thing saying I don't have that ability. I cannot tolerate network faults. I am assuming that the network is always up in this case, right? So that's all it's saying. Okay. So here is a picture that I took from the internet somewhere. It's this picture is drawn for database systems, okay, not in general any arbitrary distributed systems. And you will see there are things that you may have heard of, things like MongoDB, Memcached, BerkeleyDB, and then there are relational databases like MySQL and so on. And you will see that which properties do they provide and which ones they don't provide. So if you are in this region, for example, you are giving consistency and partition tolerance. So MongoDB will not give you availability because of this reason. And then if you look at things like MySQL, it's going to give you the C and the A property, but not network tolerance and so on. Okay, so should just give you a sense of what different systems actually do. Okay? And this is something you have to decide if you're building a distributed systems, which of those 3 properties, which 2 are more important, because you can't do all 3. Okay, that's the basic design point you want to keep in mind. Okay. So let's move on to now come back to replication and consistency more broadly. Okay, we are not going to talk about availability or partition tolerance now. We are just going to talk the remaining time about consistency issues. Okay, so what kinds of consistency guarantees can you provide to your users or to requests? That's what we are going to actually talk about, and we look at a series of them. Okay, but before we do that, I just want to give you some sense of how to even think about some of these issues. Okay. So you could ask what kinds of overheads can a consistency mechanism impose. Okay. So to understand what kinds of consistency guarantees you can provide, you have to ask, okay, if I provided a stronger guarantee, how much more overhead does it impose on the system? Okay, because ideally you want to provide the strongest possible guarantee that you are willing to tolerate, meaning that you are willing to pay that price, because every consistency technique comes with some overhead. Okay. To understand this, I am going to give a very simple example. Okay. Let us take a file, okay, or an object that is replicated. Okay. Let us just take a file that has 2 or multiple copies, okay, and we want to keep them consistent. Okay. So that means every time you write to a file and save something to the file, you have to essentially update the other copy. Okay. So now assume that the file is being read. Let's say it's an HTML file. So you're actually being read by users who are sending HTTP requests to the server. Okay. Let's say that R is the read rate. That means that there are R requests a second to access this file. Okay. It's replicated, but let's say R is the request rate. So these are all read requests. Okay. And let's say W is the write frequency. That's the rate at which you're updating the file. Okay, maybe it's a breaking news or some such thing on a newspaper site, and you are updating it every few minutes or every hour or whatever it is. That's going to be the write frequency. Okay. So one of the things you got to think about when you start thinking about the consistency overhead is what is the relative frequency of reads and writes. Okay, and that will also tell you what kind of price you want to pay. So let us assume that the file is very popular. It's being read very frequently. It's maybe the front page of the New York Times or CNN or whatever your favorite news site is. Okay? Lots of users come see it. Okay? So then if there are replicas of that web server, okay, every time you update it, you better update all the copies immediately. You don't want to have older pages being served to your end user. Okay? But because it is very popular, okay, and let us say that there are hundreds of requests coming every second, and then maybe it's updated once every 10 minutes. Okay? So the write frequency is much lower than the read frequency. Read frequency is very high, lots of requests every second, but you're updating it once every 600 seconds. Okay? So in that case, okay, you are saying that every time you write and I perform any consistency operation, that operation is going to serve the next so many read requests, which are a lot. So you want to be able to pay, you are willing to pay a price because every update is going to be seen by lots of users down the road. Okay. So you say in this case I'm willing to pay an extra price for updating the web page and keeping it consistent with one another. Now we'll take the opposite scenario. Okay, let's take a case where the write frequency on the file is high, the read frequency is not. Okay. Maybe it's your blog that nobody reads. You update it a lot, but you don't have any followers. Okay. So you might say every time I make an update, I'm going to send it to all the n replica. So you are sending all this, doing all of this extra work, but that extra work is not giving you any benefit because there are few reads that are actually seeing any benefit from it, because the write frequency is much higher than the read frequency. In this case, you might say that's too much extra overhead, weaker guarantee may be okay. Okay, maybe every once in a while a user might come and not see my latest blog post, but that's okay, nobody comes in here, something of that sort, right? So that's a scenario where you have the opposite case where the read frequency is low, the write frequency is high relative to one another. Right? So you might say in that case I don't want strong consistency guarantee, my weak ones might be enough. So this is a performance argument or an overhead argument. So thinking how much extra work are you willing to do. Okay? So you have to think of these kinds of trade-offs. Typically when many systems pick a consistency technique, they have done some performance analysis. What is the extra cost? Are we willing to pay that extra cost and things of that sort, and say this is all we can afford because it is not cheap to give you a good consistency guarantee. Okay? So keep this in mind as we go through a sequence of 7 or 8 different types of consistency guarantees you can provide. Okay? And you will see that as we go make it weaker, the overheads, we won't actually analyze the overheads, but you have to understand that as you make the guarantee weaker, the overheads also go down. So we'll start with some of this data-centric consistency model, and we'll start with the first one, which says strict consistency. Very simple to understand. It says that all copies are always in sync. Okay? There is never a copy that's out of it. As soon as you make an update, immediately update all the other copies. Okay? So you will never actually see outdated information. That's what is called strict consistency. Okay? Now it's very easy to understand, but very hard to actually implement. Okay? And there are many reasons why this is the case. Okay? So first of all, once you update a copy, okay, you have to actually send messages to the other replicas saying here is the new version of the file or new version of the HTML file. Okay. There's going to be a finite delay. You cannot propagate information faster than the speed of light. Okay. That's basically the fastest you can spread information. Okay. So you have to now think that what does strong consistency actually mean. Okay. Let's say an update is made at time t. Okay. Let's say that it takes epsilon time for that update to be sent to another machine at speed of light. Okay, that's the fastest you can send. Typically routers will buffer and it will be slower, but let's say it goes instantaneously, but still a finite delay of epsilon, speed of light delay. What if there is a request that comes between time t and t plus epsilon at that other machine? Because that your update hasn't even reached there, that request actually came after t. but it came before your update has hit that. Okay. So you cannot actually deal with this case, okay, because information cannot propagate faster than the speed of light. So this strict notion of consistency actually is not practical. Okay. So you got to relax this a little bit, saying strict with relative to I assume that I can send the message and it can reach the other nodes and so on and so forth. So it is actually much harder to provide in practice. Okay. So that's one thing you got to actually understand. It was difficult to achieve in real system. You can try, but you have to at least account for network delays, because you cannot do anything better than that. Okay. But still, every update requires lots of messages to be sent to every replica in order to tell those replicas here is the new version or the file changed and so on and so forth. Okay. So it imposes these overheads. Okay. So the next one, here is where things start getting a little hard to understand. So you'll have to go through these examples that I'm explaining, and if you don't understand something, ask. Okay. So here is a weaker version of a guarantee than strict consistency. It's called sequential consistency. Okay. So essentially, the way we are going to understand this is how are applications executing. Okay, how are they reading or writing to whatever the file is or the shared object is that you're trying to keep consistent. Okay. So what sequential consistency says is that if you are making a sequence of operations of reads or writes on one machine, okay, the other replicas are essentially going to see them in some sequential order. Okay, and so long as that sequential order essentially preserves what is called program order, which is how single program actually wrote things out. Okay, so I'm going to explain this with an example, but here is the 4 things you want. Okay, any valid interleaving of reads and writes across replicas is allowed. Okay, you have to agree on the same interleaving, and the process is going to preserve program order. Okay, so to understand this, you have to understand what is it that we are trying to do. Okay. In the strict consistency case, I only gave an example where the update went to one replica, okay, and then you try to propagate it. Now assume that all the replicas might get updates at any time. Okay, you update that file on this replica at time t, you update the same file at some other replica in the system at time t prime. Okay. So you are basically now updating it at different points in time, and then the question is, how do all the replicas see these updates that are happening at different machines? Okay. In what order are they going to see them, and how do we actually reason about that order? Okay. We'll assume for purposes of this, let's assume clocks are consistent and so on. Okay. So here is an example of what I just said. There are 4 machines, P1 through P4. Okay. This machine and then X is our shared file. That is basically you're trying to keep consistent. You essentially wrote A to that file, okay, at that time. Okay. Then at this x-axis here is time, you wrote B to that file at this later point in time. Okay. Now if you are preserving time order, then replica should see them in time in order A and B. A will be seen first and B will be seen next, because that's the order in which those writes have actually happened. Okay. But what sequential consistency says is that you can actually decide on any interleaving, okay, so long as it preserves program order. So in some sense, we are going to allow process P3 to actually see this write first, saying that update first and that update later. Okay. So you will say that B actually, the write that wrote B has happened first, and write that wrote A has happened next, and we'll still allow that, because when you actually propagate it, maybe one message went faster than the other message. Okay. So this process may say I got B is sending that message to everyone, and this process says I saw A is being sent to everyone. If these other processes see the message from P2 before the message from P1, we will still take it, okay, because that is an interleaving, so long as everyone sees it in that order, that it was B followed by A. You can't have a scenario where one machine says the write B, the notification for B came before A, and another one says I got A before B. That is not allowed. Okay. You got to agree on an order. Everyone has to say this is the order in which the writes have happened. Okay. And so long as you agree on that interleaving, then you are gotten sequential consistency. Okay. You will see that this is not strict consistency, because strict consistency would have always said everyone has to say A followed by B. Now we are letting some messages, we are accounting for some network delays maybe longer than the others, but so long as the delays are uniformly longer for every node, we are going to take that ordering. Okay, so we relax the assumption of strict consistency already. Is that clear? Okay. You will see several other things now. So, the linearizability is another property for providing guarantees, and this one says that you should have all the properties you had in sequential consistency, but if timestamp of a write is less than timestamp of another write, then the interleaving that you pick has to preserve that order. Okay, that means that if the writes are related somehow, okay, then you got to assume that you are going to preserve that property. Okay. So in that sense, it does all the things that sequential consistency does. It has one more requirement. So it is stronger than strict consistency. It actually sits between stronger than sequential consistency. Excuse me. So it is weaker than strict, but stronger than sequential. Okay. So that's called linearizability, and here is so there's a example in the book which says, let us assume now that we have not one but 3 copies of data items in a replica x, y, and z, and then you are going to set all of them to 1, which will mean that those processes have to notify. That's a write, by the way. This is a bad example because you are actually doing assignment to variable, but as what that is saying is you essentially wrote 1 to file x, you wrote 1 to file y, and wrote 1 to file z. Okay, that's all it's saying. And then you are trying to, when you say print, you are essentially trying to read the values and say what are the values. Okay. So this is our equivalent of a write, and this is the equivalent of a read. Okay, and then this basically says here is an interleaving that I will, because these operations can be interleaved in any way, we'll assume that here is one interleaving of all of those operations, here is another one, and so on. And that is what each of them are going to print. Okay. And we are going to say, okay, any interleaving is allowed so long as there is some relationship between the timestamps. And then what you will also see is you write x, that, and then when you read x, there is essentially this write has been actually read by this process. Okay, this write has also been read by this process because it's printing x. Okay, so that is, you can think of that as some implicit form of communication. Okay, you are essentially writing to a file and reading the file. That's like you sent a message. Okay. That allows you to then order, because that's like sending and receiving a message, and then you can essentially use this notion of logical timestamps to order those reads and writes. And so long as you have relationship between reads and writes across processes, you got to preserve that property. Otherwise, you can pick whatever interleaving you want. Okay. So that's what linearizability says. I think I have some more examples. Okay. So let's understand linearizability with the same kind of and causal consistency with the same example we started off with the sequential consistency. Okay. So this is related to linearizability, but it says that causal consistency as causally ordered writes must be seen by all processors in the same order. This has similar idea to linearizability. So you should ask, what does it mean to be causally ordered write? Okay. So essentially, if you say if process 1 sends a message to process 2, okay, and you got to essentially preserve the operations of those 2 operations in that order. Okay, any operation before the send cannot occur before any operation after the receive. They have to actually preserve that order in whatever interleaving you see. Okay. That is shown in this example, very simple example, where you have this shared file x. Okay. You wrote a value a to that file. Okay. Process P2 then reads that file and it sees a. Okay. That's an implicit message that has gone from P1 to P2, because it's like I wrote to a shared buffer and I read that shared buffer. So that's a message. So now think of this as a message has gone from here to here. Okay. And then subsequently, after you read this file A, you write B to that file. Okay. So you update it with some other value. Okay. So these 2 writes are said to be causally related, because there is essentially a causal ordering as a result of communication between those 2 processes. Okay. So now if you pick any interleaving, okay, you must actually say that this write has occurred before that write because they are causally ordered. Okay. You cannot actually say, you cannot see this, okay, because you can't say B has actually occurred before A, because that is violating causal order. In sequential consistency, we said you can essentially pick an order, whatever you want. and that's okay. Okay. Here we are saying if the writes are not related, if there was no read here, then you can do that. You can say B happened before A. But once you actually have this read, that implies that you essentially sent a message from here to here, and now this event, this write has happened after that read has happened after that write. So these two writes are now ordered. So this write has actually happened before that write. So your interleaving that you pick has to preserve that ordering. Is this making sense or not? Okay. So this is not going to be permitted. You cannot no longer say B has, this process cannot, if it reads a file, if it sees the value B and then it sees the value A, that does not meet our requirements of causal consistency. You must actually see A followed by B always. Okay. However, if you remove this read, okay, which is that second example, those two writes have no causal ordering. They are concurrent events. There's no message going back and forth. So if you use vector clocks or any of these things, you cannot say those two events are related. They are independent event. Okay. If they are independent event, then anything goes. We don't actually care. You can pick any order you want. In particular, you can also see different orders because they are concurrent. We don't order them. So you can see them in different orders on different machines. Okay. So this will be allowed where you essentially see, if you read the file twice, this process sees B before A, and this process actually sees the value A in the file followed by B. Because they are concurrent, we are not ordering them anymore. Okay. So you don't even have to agree that those two writes have happened in any order. In sequential consistency, you have to pick an order. It could be arbitrary, but you picked one. And everyone saw it in this order. Here we say only if they are causally related do you have to respect that order, otherwise you don't even have to respect it. Okay. Is this clear? Any questions on this? Yes, your question.
In terms of that very concrete example of coding in Python or something, what is causal consistency giving me?
Okay. If you're coding in Python, what is causal?
I'm just trying to make sense of what is this giving me
Right.
that I care about.
So I don't think it has anything to do with coding in Python. But what it is saying is, let us say, again, let's go back to our web server example, right? So in our web server example, if you, let's say, update, you have replicas of the website. Let's say there's one HTML page, you're trying to update it. Okay? So I update it on one replica, then I make another update on another replica, and so on. And then you can ask, in what order are clients seeing these updates? Okay. Right? So if you read that web page on the first machine and then you again read it again, what order are you going to see them? That's a way to think about it. So here it says, if I read, so if I basically write A to my HTML file, and for whatever reason this replica actually reads that file and then it makes this thing, all clients should see the A in the file before they see B. That's all it is saying. Okay, but if they are not actually, these two machines don't communicate, different processes can see different things. So this client could say that you wrote A in that HTML file, and then if I read it again, I see B. Here I see them in the opposite order. I see the updates being flipped, and we are still going to say that's allowed by causal consistency. That's a way to think about all of this. So the thing is, if you make updates and I'm reading those replicas, in what order am I seeing the updates? So that's basically, so web example is a good one to think about. Okay. Any other questions here? Okay.
So this
Yes.
is just a stricter version of the sequential consistency.
Is it a stricter version of sequential consistency? Actually, it's weaker version than sequential consistency, because the reason it is weaker is it's saying that if the writes are not ordered, I can show different orders. Yes, yes, yes. That's right. So it is, we are weakening it one step at a time. Okay, so it's actually weaker than some of the other things we have talked about. Okay, and there are many others which I'm not going to go into. There's something called FIFO consistency. It says I don't even care about interleaving writes across machines. Okay, just essentially says that if one machine is making a sequence of updates, just respect that ordering and don't worry about how you interleave them across processes and so on. So if I make an update on this replica followed by another update on that, the same replica, just make sure those updates are ordered. So they're FIFO on a per machine basis, but then I don't care about anything else. Okay, so that's actually an even weaker version of this. and so on. Okay, so I'm going to, and then there are other ways to think about consistency. It's a thinking of it on a per write basis is far too complicated. We can't actually understand what's going on, etc. Let's not worry about all of that. Let us just have specific times in points in time where we make all the replicas consistent. So we'll say at time t, let's sync all the replicas. Everything is consistent. Okay, then they will diverge for some point in time because some updates may have occurred, and let them diverge. And then some at other point in time, we'll again say synchronize, and everything becomes synchronous again. Okay. So if you just use these points in time where you make them consistent, you have a very weak form of consistency. Okay. And this actually is used in many cases in programming language. When you write code, you have things like entry and release consistency for your critical section. Okay. When you enter a critical section, you assume that everything is consistent. Okay. And then when you are making changes, things might get out of sync again. But then again, when you are exiting, you might make things consistent again. Okay. So there are points where things will diverge, things will be inconsistent, but you let them diverge. Okay. So there are many different models like this, and many of these models exist because maintaining any of those more consistency guarantees is actually hard. Okay, so you will see that most systems don't even bother to do most of what we talked about. Okay. But here's a table that just shows you, okay, how you start from the top and how. So strict consistency is the strictest one, then linearizability is the next stricter, and then sequential, then causal, and the FIFO is the weakest one. And this one is actually looking at it saying we are not going to think of consistency on a per write basis, too complicated. Let's look at it at different points in time. Okay, so your entry consistency says whenever I enter a critical section or some such thing, I will make things consistent. And then release says when I exit the critical section, I'm going to synchronize my replicas and so on. Okay. Yeah, question.
When I say I get sequential consistency, do I only need to get it from client's perspective? Because the replicas themselves, they will see different order.
Yes.
So
yeah, the question that is being asked is, when I see sequential consistency, should I only see it from the client's perspective? That's what you're asking, right? So the way these consistency models are written is there are n machines in the system. So from the perspective of your question, you can think of some machines are servers, some machines are clients. Okay, in sequential consistency, we don't actually distinguish between them. So if you, because all machines have to agree on that order. So if clients are seeing them in certain order, the servers, if they happen to read that file, should also see them in that same order. Okay, so we'll assume that is the case. But yes, so the short answer is yes, clients will see them in that order, but this requires that all machines, which include servers, also have that same order if they happen to read the file or some such thing.
can you actually implement sequential consistency then? Because you really need to know the network latency, how long it takes,
Right.
propagate before it can read it.
Okay, that's a good question, saying can you implement sequential consistency? Okay, so the thing you got to remember is we only talked about what kinds of guarantees would you like to give to users. We did not talk about how to provide the guarantee. We not talked about a single algorithm that gives any of these 7 things we talked about. Okay? So we have only talked about semantics, not methods or mechanisms to do it. Okay? We will come to mechanisms later, but we won't actually do all of them. We'll only see some of them. So the short answer to your question is there are techniques that will allow you to give sequential consistency. They are actually used. They are fairly complicated, but they are there. We have not talked about it. We only talked about what the concept is, not how you can implement it. That's the thing to keep in mind. Okay? So the only 2 concepts we are going to look at is the strongest one and the weakest one, and say how do you do those 2, and all the ones in the middle, we will leave that as homework. Not real homework, but if you're interested, you go look at it. Yes.
When we talk about the CAP theorem, which one are we talking about?
When you talk about the CAP theorem, which consistency model are you talking about? So in the case of CAP theorem, it is actually assuming the stopple. Because once you lose consistency, you are in the land of nothing, not strict. Anything else is not strict. Okay?
So wouldn't it make more sense to formulate the CAP theorem in terms of gradations of all these things?
Okay,
rather
question.
than just the strictest sense of it?
Right. So the question is, should you reformulate the CAP theorem by saying under these scenarios you can actually provide this type of consistency? You could. I'm sure that there are papers that have said you can't do strict, but you can do this. There will be lots of papers on this topic. Right? The original CAP theorem simply uses a very simple notion. Consistency means strict, because that's what you mean by consistency when you talk about consistency. Right? If it's not strict, then you got to qualify what are you actually talking about when you talk about consistency. Right? So yeah. Okay. So there are many other models as well. I'm not going to go through the details of this. So these are actually, I thought I have a picture here of client-centric consistency. So this one that goes back to the question that was asked, because in all of the models I talked about, there are n nodes. We don't distinguish between clients and servers. Okay? There are models that are written purely from a client perspective, saying I am a client. Servers are making some updates. In what order am I seeing? Forget what order the server sees. Okay? So those are called client-centric models. Okay? And these client-centric models should work regardless of if the location of the client changes. So if I read a file here, okay, and then it shows me some version. I go home, different network. I read the file again. Maybe that read goes to a different replica. Okay? So what should I see there? Yes, so that is now looking at it from a client's perspective. A client is making requests one after the other in time, but its location might change. It might go to different replicas at different point in time. What am I going to see? Okay? So those are these models, and so the monotonic read says, once I read a copy of the file, I can only see a newer version. You can't show me something older. Okay? So I read the New York Times here, I go somewhere else, maybe some cache is serving me the new copy. I can't see an older page. I should only see that page or a newer page. So you see monotonically newer versions, never an older version. Okay? Monotonic writes is so it's sort of the same concept from a write perspective, saying basically it's like FIFO consistency, saying a write must actually hit all the replicas before the next write hits. You can't actually have writes jumping over on older writes and so on. Okay? And then the same kind of stuff. Read your write says, if I write something, I should be able to then read that or a newer copy. Okay? And write follow read saying is the opposite. Okay? So read your write is actually an interesting problem. Sometimes you will actually see this happening because systems don't actually do read your writes. So you can try this actually on the EdLab. You can go on one machine and change the password. Okay? You modify your password. Okay? You go to another machine. Okay, and try to log in, and sometimes it won't log you in with the new password. Okay. The reason is on that machine, the replica, the password, there are multiple copies of the password database. Your password database is not strictly consistent. It is using a weak form of consistency to propagate your password updates. Okay, so as soon as you change a password, one copy is updated, but all the other copies are not yet been updated. So if you go to another machine that is talking to a different password database replica, your new password hasn't yet reached there, so you will see that you can't yet log in there. Okay? So that means you did not read you wrote something which you wrote a password, a new password to the database, but when you're trying to actually log in, it's reading the password and checking what you're entering. You don't get that property. Okay? And that's not what you expect. You say, I just changed my password, I cannot log in. You don't expect that behavior. Okay? That's because most of the systems don't do even very simple things that are not even strictly consistent. They actually are doing something much, much weaker than any of these properties that we talked about, which is called eventual consistency. Okay? So eventual consistency is what many systems do. Eventual consistency says no guarantees. Everything will get propagated eventually. We don't say how long it will take, when systems will become consistent. They will keep doing something and eventually everything will be good. So that's basically no guarantee at all. Because consistency is hard, many systems just don't bother. Okay? They basically will do something to propagate updates, but don't give you any guarantees whatsoever. Okay? That's unfortunately the state of most of these large-scale systems because of the expense of providing any consistency guarantee. So DNS does this. Okay? I just talked about password databases that do exactly that. Right? So it says one user changes the password on one machine, that user goes to another machine. The password is not updated on the other machine, okay, because weak consistency. So eventually your password will show up there. Okay, how long it will take, no guarantees. Okay, it might take some time. We don't actually even bound that time. Okay. So essentially what eventual consistency means, okay, the formal terms is as if you stop making updates to your files, eventually all the replicas will converge. Okay, so you say, okay, I made all the changes I want, now you just sit. Okay, and then the replicas will keep doing something, and after a while they'll all converge to all one copy. Okay, they'll eventually become consistent. That's what it means. Okay, so essentially that is what the meaning of eventual consistency is. So very cheap to implement because you're not giving any guarantees. Lots of systems do this. They'll do pairwise update. I'll talk about several techniques on how to do this. Okay, and they will actually get us there. Okay, so things typically what this means is if you're accessing the same replica, things are fine because you made the changes that replica seen it. If you go somewhere else, try to access another replica, that laptop moves somewhere else because your changes you just made will not be visible. Okay, because they won't actually are propagated often. Okay. So in the last 5 or so minutes, I'm going to introduce a technique to implement eventual consistency, which are called gossip protocols or epidemic protocols. If you have taken graduate databases, you may have done gossip protocols. I don't know, maybe they don't teach it or teach it, I'm not sure. But I'll talk about what these means. Okay, so essentially the way these eventual consistency protocols work is modeled, not really modeled, but can be thought of as how diseases spread. Okay, so let's say you are infectious disease, you have cold. Okay, and then how does your cold spread to someone else? Okay, you basically go shake someone's hand. Okay, then you basically infected that person, or maybe you go and sneeze but don't cover yourself or something, and then you infected someone else. Right? So and then that person is going to do the same thing. Okay? This is called pairwise exchange. Okay, so the way we are going to essentially, just as diseases spread through infectious diseases spread to pairwise contact, so will our updates propagate in the system. There are n replicas. Okay? Every once in a while, 2 replicas will connect and say, do you have any updates for me? Okay? So here the machine will say, here, I got some new files, take them. Okay? So that second machine now has your file. Okay? And this will continue. So essentially, any update you make will keep spreading through the system through this pairwise exchange. Okay, and the hope is after a while, all machines get infected. So everybody has the file. Okay? But just as in infectious diseases, there will be some random chance that some people don't get infected because they don't come in contact with anyone who's infected. So they will remain not infected. Right? Same is true here. If a server never actually talks to an infected server, which is a server that has some changes, it will never see the update. Okay? So in the limit, there's always if you do random exchange, because the randomized algorithm, there's always going to be some non-zero small probability that an update will never reach some small subset of replicas. Okay, but by and large, this is how we are actually going to do this. So it's basically based on the reason they're called epidemic protocols is they're based on theory of epidemics of how diseases spread, infectious diseases spread, and so on. Okay, so there's some terminology. There's an infective store, which is a replica that has some changes that it wants to tell others about and spread the update. Okay? A susceptible store is not a store that has not yet seen it. It needs to be infected by the infected store. And then we are going to see many variants of this. Okay? So there's something called anti-entropy, which is what I just described. That's a fully randomized algorithm. Okay? If you have n machines in the system, server P randomly picks another server Q and asks it for changes. Okay? Here you can do push, pull, or both, saying, give me your updates. That's pull. You can contact a random server and say, here, I got some updates for you. That's push. Or you can do pair by saying, give me your updates and I'll give you mine. And they will basically essentially exchange updates. Okay, so you can do push, pull, or both. And there is a small claim here saying a pure push-based approach is not going to spread things quickly enough towards the end. Okay, so the reason is if you had a pure push-based approach, okay, you are the infected store, you contact some other machine, you basically give it its update, and then it will push its update and so on. But after a while, there will be some small set of servers that have not actually been contacted. If you keep pushing, you might still keep talking to servers that have already seen the update, so there's nothing to push. Okay. Pull is the opposite. Okay, pull is slow to start, but it's good at the end. Because if you basically have only one machine that has seen an update to that file, all other machines have the previous version of the file. If you pick a random machine and say, do you have a new copy? Initially, that machine would say, no, I have nothing to offer. Okay, so you might be asking lots of machines and they will all say, I haven't seen no change to this file. Okay. So at the So when you have anti-entropy, push is good to get the update going quickly, spreading through the system quickly. Pull is good to essentially ensure that the last few machines that have not seen it will actually see it, because towards the end, if a pull machine contacts a random server, it is likely to have already seen the update and you can pull it. So if you put a combination of the two, that randomized technique actually works much better. Okay. That is called anti-entropy. Okay. There's another variant of this which is called rumor mongering, which is basically how you spread rumors. Right. So it is basically a push protocol. As you can imagine, you heard of some nice piece of gossip. Okay, you call 10 friends and say, here I heard something about such and such. Right. So essentially again random way to spread. So you are going to call your friends. Your friends will say, oh, this is great. Let me tell 10 other people, and then this rumor is going to spread. But after a while, you are going to stop, because you say, I have already told everyone. I think everyone by this time knows that such and such thing has happened, and you are going to stop. Okay. So essentially, all this rumor mongering have a probabilistic back off, saying, I think everybody knows this is common knowledge, not worth calling 10 more friends and telling them about this. Okay, so essentially, what you do in this case is you will toss a coin after you talk to every one of your friends, and with probability 1 over k, you will stop. Okay, and the k is going to tell you how aggressively you spread the rumor, or do you only tell a small group of friends, or do you tell a large group of friends, and so on. So because you need to stop at some point, you can't keep repeating the same things once your friends have heard it. Okay, so essentially, if an item is hot, you are going to keep spreading it. Once gossip news becomes cold, you want to stop spreading it, and you are going to use a randomized way to decide when to stop. Okay, so again, pairwise exchange. Okay, and this is basically another variant of anti-entropy. And there's actually, if you look at the book, there's a small analysis that shows with that exponential probability. It's a very low probability, where k is the number of k is the probability with which you essentially stop spreading the rumor, and s is the number of replicas that have not yet seen that rumor. So after some number of attempts, that's decay exponentially, but there will be a small non-zero probability that somebody is not yet heard that rumor. Okay, they are not talking to anyone or some such thing, so they will not have seen it. So there's always some chance of having susceptible stores that never see an update. Okay, this is why it's eventually consistent. You have to remember, there's no guarantee that it will take it might take an arbitrary amount of time for things to become consistent, which could be infinity in the limit. Okay, is this clear what we talked about? So now you will actually, if you think about it, lots of systems that you have thought about actually use this model. Okay, and you probably encountered this system. You can think of Dropbox. Okay, Dropbox does pairwise exchange. Okay, there's actually a Dropbox server. All your devices, whenever you make an update, at some periodic interval, your machine is going to tell the server, saying, here, I will push my changes to you. If some file was updated on some other device for that user, I will pull it. Okay, that's an example of pairwise exchange. And there are many such things. Anytime you have cloud storage that is synchronized across machines, they are all using some form of eventual consistency. Okay. Source code control repositories also do the same thing. Right? So you basically, when you have things like Git repos, you are going to push changes, you are going to pull. Okay, there's no guarantee that as soon as you push a change to the Git server, everyone else who is actually checked out that repository will get updated. They'll eventually hopefully push or pull, and things will actually become consistent eventually. Right? So all of the systems we think about and which use replication, they all use this form of pairwise exchange. Okay, so you basically update your contacts on one machine. Same thing, it will go to a calendar contact server, and then hopefully it will propagate to all of these other machines. So this is how most systems work. Okay, so we start with strong consistency, but this is what many of the systems end up doing because it's cheap to do. There's no guarantee to provide. So things will be inconsistent for some period of time, and for those applications, it's okay to stay inconsistent. Right? So it's as soon as you update a file in Dropbox, you don't assume that instantly it will appear on some other machine. You are willing to tolerate a few seconds, few minute delay before things get up to date, and for those applications, that's okay. For some other applications, it may not be okay. Then you've got to think of stricter consistencies. Any questions here? We ran out of time, so we'll stop here for today. Okay, so again, thanks for coming on a Friday. I'll put the class for everyone else on YouTube, and we'll continue on Monday. Okay, so